Hello everybody, my name is Philip Johnson. Today I'm going to go over Physics Lab 5, Choose Your Own Adventure. My adventure of choice was to use high-resolution baseball footage to discover the force with which Marco Scutaro hits a baseball from a major league pitcher. The video observed was of a line drive in an actual baseball game. To do our analysis, we'll be using Newton's second law and the momentum principle, as well as a tracker video. In detail, we'll use position data from tracker to derive forces and momentums, most importantly, force at the point of contact. Our result was that Scutaro hit the ball with over 1,000 pounds of force. Let's see. The momentum principle is the operative principle in this physics experiment. We'll use the position data to derive momentums in our computational model. Pause the video to observe the relevant forms of the momentum principle if needed. Note most importantly that Fnet is equal to dPdt. If we can find the components of momentum based off of the data provided for our baseball, we can then find the Fnet exerted on the baseball at different points through its flight. Let's move on to see the video in tracker to try to provide context for the experiment. This high-resolution video, shot with a 750 frames per second camera, shows the moments before and after a swing from Scutaro. As we always do with tracker, I marked the movement at the center of the mass of the ball along each point in the path. I made sure our units would be in meters by calibrating based upon the measurements for the baseball and putting that calibration in meters. It's worth noting that unlike the collision discussions in our class using the energy principle, the system for the experiment is the baseball and only the baseball. I made this choice of system for the utility of being able to consider the force from the bat as a force from the surroundings versus a change in energy among the system. I found the former calculation easier, so I chose this system. Note, however, that there will still be conservation of momentum if we were to choose the bat and the ball to be the system, due to the law of conservation of momentum. Let's go to our initial conditions. The ball mass is standardized in Major League Baseball at 0.156 kilograms. We used the 76 millimeter diameter of the baseball to calibrate. We converted it to meters though, so we could get our units in meters. The time step produced by tracker is 0.1 seconds between each frame. However, the source that I got the video says that the camera was 750 frames per second. We have to be careful to put this in our model, or else we'll get very strange numbers for velocity. Also, baseball.csv has our data from tracker. I spelled baseball weird because I felt like it. Again, our model does not predict where the ball is going. That is read from the CSV file. Our model instead will read these positions showed on the screen, all the while crunching calculations on momentum and force. The most important calculation, or the one of interest in the experiment, is the force when Scutaro hits the ball. Let's get to the actual computational model. This code is very much adapted from the black hole lab that we did earlier, where we derive forces from position data. In any case, I set the ball mass as mentioned, and I set the delta t to the 750 frames per second measurement mentioned earlier. This is different than tracker, where it has 0.1 between, and what I've put is actually correct because that's the actual time in between frames of the camera. I started the time at 0, there's a loop to read the position data, and then here we use that data to find velocity, momentum, change in velocity, change in momentum, and thus dPdt, and thus Fnet. Note that Fnet and dPdt are broken down in parallel and perpendicular components. We're not really using that so much for this lab. We're more interested in the actual Fnet. However, it is done here very similar to how it is done in the black hole lab. The main difference between this code and the black hole lab is that I know the exact frame where Scutaro actually hits the ball. The result is that when we have iterated into that data point, I output the Fnet so I can see the Fnet at the time of contact. Let's actually run the computational model to get a look at what we have. As we can see, it models the motion of the ball pretty decently based off the hit. I output the velocity of the ball. It's moving about 40 meters per second. That's about 90 miles per hour. That's about right for what we find in a baseball pitcher's repertoire as far as speeds. As you can see, sometimes there are big variations in speed. It could be due to inaccuracies in marking tracker, but overall it's about 90 miles per hour. Here's where I output the force, the net force when it was hit. It was about 6,000 newtons. That's almost 1,300 pounds force. Scutaro hit the ball pretty hard. After he hit it, we see the velocity in the other direction going about 100 miles per hour. It's pretty quick. Let's do a quick sanity check. Is all this reasonable? The ball was traveling about 90 miles per hour, and after it got hit, about 100 miles per hour. Looking at past experiments that others did with a baseball and a baseball player hitting it, these are pretty reasonable numbers. However, there are definitely some limitations to my model. For example, there are obvious inaccuracies because there's air resistance and gravity. The net force that I found isn't only because of his bat, there are other forces operating upon the ball as well. In this case, I ignored both of these because the majority of the force is going to be from the baseball player hitting the ball as hard as he can. So he found the force from the bat, the intended result of the experiment. But so what? What kind of questions does our analysis answer? What kind of questions does it pose? First question I brought up was, how does hitting the non-sweet spot of the bat show conservation of momentum? Let me show you what I mean. In our clip, Scutaro swung and hit the ball such that his bat did not vibrate or break. Instead, most of the energy with which he swung actually got transferred to the ball, and he hit the ball very hard as a result. However, other times, baseball players will swing just as hard as Scutaro did, and they'll get different results. For example, their bat will break, or sometimes their bat will obviously vibrate afterwards. Instead of the energy getting transferred to the ball, there's still the same amount of energy in the system. However, it gets transferred into vibrational energy, and in some cases, the vibrational energy is so much that it breaks the bat. The point is, energy is always conserved. Or better put, it is conserved between system and surroundings. It's very important that I word it that way, so you don't take away points. My other question was, does throwing the ball faster increase the force which the batter ultimately hits the ball? Maybe it'd be advantageous to not throw it so fast. I mean, we all know that if we threw a tennis ball as hard as we could against a wall, that it would then bounce much more than if we threw it much slower. I got this idea from the fact that Newton has this third law that says whenever there are two forces, there's an equal and opposite reaction to that force. All forces are interactions between different bodies, and they produce equal and opposite forces. However, looking at the bat is not a brick wall. Depending on how you hit the ball with the bat, your bat can break, it can vibrate, energy can be wasted. As a result, it's sort of irrelevant. But of course, there's always conservation of momentum in a collision. This concludes my lab. Sorry that I went a little bit over time. Be nice grading. See ya.